In this video, we're going to talk about different operations that can be performed on functions. In particular, we'll see how it's possible to add, multiply, and compose functions defined on the real line. If we take two numbers, x and y, and here x and y are just arbitrary real numbers, then it's of course possible to add them together. Addition is a well-defined operation on real numbers. If instead we consider two functions, f and g, where f and g are both real-valued functions, that is to say functions that take on real number values, it stands to reason that we should be able to add those functions together as well, since, after all, their outputs are just real numbers on which the operation of addition is already defined. In fact, we should be able to subtract functions as well, since subtraction is really just another form of addition. The way this plays out, to be more precise, is as follows. We begin by choosing a number x that belongs to the domain of f and the domain of g. Then we compute the value of f at x and the value of g at x. And then we simply add those two values together. This defines the value of a new function at the input x. And once again, the value of that new function is simply the sum of the values of f and of g at x. By doing this for each individual input common to the domains of f and g, we end up defining the function f plus g, the sum or the addition of the two functions f and g. So the operation of addition defined on real numbers naturally extends to real-valued functions. And one way this can take on significance in real life is via the classic formula from economics or from business that says that profit equals revenue minus cost. Indeed, if you are the owner of a business, then you might find it helpful to actually model profit, revenue, and costs associated with your business by real-valued functions, p of x, r of x, and c of x, respectively. Here the input x might represent the number of items that your business produces, and the output of these functions would of course be some monetary value. And what you could do is figure out the cost of producing x items, the revenue or the amount of money that you would take in through the sale of x items, and just by considering the difference of those two functions, arrive at a new function that describes your profit. And you might then go on to try to figure out how you should choose the number x so that your profit is maximized. Let's move on to another operation. Just as two arbitrary real numbers x and y can be multiplied together, so too can two arbitrary real-valued functions. And the principle here is the same as that for addition. Since multiplication is a well-defined operation on real numbers, it extends naturally to an operation that is defined on real-valued functions. Indeed, since division is just another side of multiplication, or if you like, the inverse operation to multiplication, it is also possible in the same way to take two functions and divide one by another. An operation which is well-defined as long, of course, as the denominator, g of x, is not equal to 0. Here, once again, the principle is the same as before. For any value x that is common to the domains of f and g, we can simply compute the values of f at x and of g at x and multiply them, or if we like, divide them, thus producing a new function derived from the functions f and g. There's a third operation that we're going to discuss in this video, which is perhaps the most subtle and also important of the three operations. And to get a feel for how it works, imagine that we have three different sets called A, B, and C. Imagine furthermore that we have a function, let's call it f, from the set A to the set B. And also a function, let's call this one g, from the set B to the set C. Well, there's a natural way that these two functions can be made to interact. And to understand how that works, let's imagine that we choose some point x in the set A, which in our picture is denoted here by a white dot. what we may of course do is take the function f and apply it to that element x, thus producing an output or value f of x inside the set B. And since f of x is an element of B, we can in turn take the function g and apply it to it. We can compute, in other words, g of f of x, thus obtaining an element inside the set C. What this allows us to do, if you think about it, is define a new function from the set A all the way to the set C, simply by applying the functions f and g one after another. And this new function is what's known as the composition of the functions g and f. The notation for this, which you'll often see written in textbooks, is to place a small circle in between the names of the function. So here, g composed with f in that order will be a function from the set A to the set C. And for any element x in the set A, the composition, g composed with f, will be defined as g of f of x. Or, to be a bit less informal but perhaps more descriptive, the composition of g and f is obtained by taking the function f and sticking it inside of the function g. In case the composition of functions sounds like a very abstract or rarefied idea, let's take a minute to make things a bit more concrete. Suppose that you're in a hot air balloon that's rising up into the sky, and that you hold in your hand a thermometer which you use to make temperature readings as you move through space. There are multiple variables at play here if you think about it. One of them will be the temperature that you measure with your thermometer. Let's call that H. We can imagine that the letter H stands for heat. There's also the altitude of the hot air balloon, which is changing in time. Let's call that A. There's also, of course, time itself, T, which is steadily ticking onwards. And if we think about how these variables are related to one another, we'll see very quickly that they are linked together in a sort of chain. Indeed, the temperature H is a function of the altitude A, which is itself a function of time T. And so you see, what we have on our hands here is precisely a composition of functions. The function A of t is sitting inside, as it were, the function h. The function a takes values of time and associates altitudes to them, and the function h takes values of a, or altitudes, and associates temperatures to them. So that ultimately, h can be realized as a function of t. This is how the composition works. Let's finish up by reviewing the operations of functions that we discussed in the context of functions that are given by algebraic formulas. So let's assume that the function f of x is defined by the formula x cubed, and the function g of x is defined by the formula radical of 1 plus x squared. If we were asked to produce a new function that represents the sum of f and g, then we could simply write down a new formula, and let's call that new function h of x, that's obtained by adding the formulas that define f and g, just like so. Likewise, if we wanted to produce the product of f and g, then the thing to do is write down a formula obtained simply by multiplying the formulas that define f and g together. To compute f composed with g, we would want to take the function g and place it inside of the function f, like so. And the way that this would play out concretely is that we would take the expression that defines g and substitute it into the variable x in the defining formula of f. So this would give us radical 1 plus x squared, all raised to the power 3. Right, so here we take a number x and apply g to it to obtain radical of 1 plus x squared, and then we apply f to the result, which entails cubing radical of 1 plus x squared. We could also, of course, try to compose these two functions in the opposite order. We could try to consider g composed with f. And that would entail taking the function f and placing it inside of the function g. And the precise value of this formula is one that I will ask you to think about on your own.